All right, let's keep going with our quick review. We're going to jump into Unit 5 and 6 here, which is exponential functions. So we know exponential functions have to do with repeated multiplication, which is why we have an exponent as our variable. So equations in the form y equals a times b to the x. We know that a is our initial value, and b is our factor. And this factor can either be a growth factor if b is greater than 1, or it can be a decay factor if b is between 0 and 1. So let's take a look at example 1 here. Consider the function for cell duplication. The cell duplicates every minute, and we have f of x equals 65 times 2 to the x power. What do the values of 65 and 2 represent in relation to the duplication of these cells? So we just talked about this. The number out in front is our initial value, so this is the initial number of cells. And the 2 is our factor, so we are multiplying by 2 every minute. In addition to this exponential model, we also had a similar model that was for exponential growth or decay, and it was a equals p times 1 plus r to the t. A is our amount, our final amount, and our initial amount is p, our rate is r, and all of this together is our factor, b. So let's take a look at example 2. Juan has a savings account. The total amount of money in the account in relation to the time in years since he made his first deposit can be described by the equation A equals 2,500 equals 1 plus 0.03 to the t power. Identify what each part of the equation represents. So our initial deposit is going to be this value out front. So we started with $2,500 initially. The growth factor is the total inside, what we're multiplying by each time, which would be 1.03. The time is represented by the variable t, and it's every year. So this increases by 1 every year. And then our interest rate is just the r value on the inside, which would be 0.03, which as a percentage would be 3%. So in example 1 here and example 2, we're just identifying parts of the different equations that we can have for exponential functions. Let's take a look at example 3. The table shows an exponential relationship between the number of employees working for a business based on the time in years since the founding of the business. All right, so here's what we need to remember about this. This p value, this a value, our initial value is when t or x is 0. It is the y-intercept. So we need to be able to identify that in a table or on the graph if we're trying to identify what our p-value or a-value are. So if we look at this table, we can see that we do not have the y-intercept here. We do not know what the initial value is, but we do see how it is changing from term to term, and we can identify that factor. We can find b by taking any term and dividing it by its previous term. So if we take 800 and divide it by 640, we get 1.5. If we were to take 1.25. If we were to take 1,000 and divide it by its previous term, 800, we'd get 1.25 again, which means that as we go from year to year, we are multiplying by 1.25 each time. It's our common value, or our common ratio. The problem here is we don't know our a value, because really we want our table to start with a 0. So we have 1,640, 2,800, 3, 1,000, and so on down that list. But really, for our initial value, we need to know what goes at 0 right there. So we're going to have to work backwards. So if we are multiplying by 1.25 to go forward, to go backwards, we're going to be dividing by 1.25. So if I take 640 and I divide it by 1.25, it will tell me what it was before. So in the calculator, 640 divided by 1.25 comes out to be 512. So this is our initial value. So if we're going to create an expression here, we're going to have y equals, or you can do f of x equals, it doesn't matter, f of x equals 512 is what we started with, 1.25 is what we're multiplying by, to the x power. We can verify this in Desmos. We're going to go in and we're going to put the table that they gave us. So 1, 2, 3, 4, and 640, 800, 1,000, and 1,250. And we are going to use our model, y equals a times b to the x, and we're going to alter it just a little bit. We're going to do y1, and then our tilde, a, b to the x1. And what that's going to do is that's going to give us our exponential regression to tell us what our a and our b values are. So again, we're going to do y1 is approximately equal to a times b to the x1. I need my 1. There we go. And when we do that, we can see that our a value is 512 and our b value is 1.25, which is what we put into our formula. So just like we did linear regressions in Unit 7, we can do exponential regressions right here in Unit 5 and 6 to find equations if we have tables. You just have to make sure that you use the correct model. Let's move on and take a look at the graphs of these exponential functions. We need to remember that we're going to have a line that a line that curves. It approaches, start over again. We're talking about an asymptote, which is a line that a curve approaches as either x or y coordinate increases towards infinity. So what we're looking for is where the graph flattens out. So our graph gets flat there, and it's flattening out as it approaches the value of 1. So there's our asymptote. So let's think about what this could look like. We could have a situation where we have an asymptote and it is growth, right? We could have a situation where we have an asymptote and it is decay. We're most familiar with those, but keep in mind that we could also reflect those. So we could have an asymptote where we had growth, but it was reflected over the x-axis. So it's going to open down like that. Or we could have an asymptote that was originally decay, but it is going to flatten out and be upside down like that. So there are 4 options for what these graphs could look like with our asymptote. And right here in this example, it says to sketch the graph that represents this description. So it's an exponential function, so it's going to look like one of these 4 things right here. And it has a y-intercept of 2, an x-intercept of -3, it is always increasing, and it never reaches 4. So what that's telling me right there is that there's an asymptote at 4. And if it's always increasing, I'm going to have to be getting closer and closer and closer to that, but never getting to it. So this is always increasing because this is uphill everywhere we go, but it's never going to cross 4 or get to 4. All right, so let's talk about end behavior. Remember, end behavior is what happens to the graph on the left and the right. So left we represent as x goes to -infinity because here's our x-axis and -infinity is this direction. Right would be x goes to +infinity. So we need to describe what happens in both of those situations. So as x goes to the left and as x goes to the right, we need to make some statement about what happens to the graph. So for exponential functions, the graph is either going to go up forever, down forever, or get closer and closer and closer to that horizontal asymptote. Here we have a horizontal asymptote at y equals 3, and we can see that on the left side, as we move left, it flattens out onto the asymptote. So as we go to the left, our graph gets closer and closer to 3. As we move to the right, towards x is going to infinity, our graph is getting bigger and bigger, and will get bigger and bigger forever. So y is going to go to infinity. So that is a review of end behavior. And finally, geometric sequences. Geometric sequences are different because instead of counting with our initial value at 0, our first term has an input of 1. So if we take the sequence that we have here, the first term is 9, the second term is 27, the third is 81, and 243 is our fourth term. So we can write an explicit form right here. AN is equal to the first term, 9, times what we're multiplying by each time. And we can find that again by doing any term divided by its previous. So 27 over 9 is 3, 81 over 27, also 3. So we're multiplying by 3 over and over again, and then we just put n minus 1 up here as our exponent. We can write an exponential model here that doesn't use the sequence, but in order to do that, we need to know what the 0 term is. So we already know what the first, second, third, and fourth term are, 9, 27, 81, and 243. But to use this, our a value has to be the result of the 0 term, or the y-intercept. So if we're multiplying by 3 to go this way, we need to divide by 3 to go the other way. And that's going to give us 9 divided by 3, which is 3. So our exponential form would be our y-intercept is 3, our initial value. We're still multiplying by 3, and then we just put an x up there at the top. So there's our equation there.